Hey guys, I want to welcome you back to our Introduction to Acids and Bases part of Unit 15 here. And we're just going to kind of dive in a little bit and talk a little bit about how chemists like to be able to categorize things into different groups. And one way they did that is with acids and bases. Now, a long, long time ago, acids were just simply considered things that were sour. They turned litmus red, and they eroded metals, which caused hydrogen gas to be created. And so these are things like you see here: stomach acid, lemon, grapes. I mean, citrus fruits. Milk, interestingly enough, has lactic acid in it, which makes it acidic. Okay. Bases, on the other hand, were categorized as slippery. They turned litmus blue. And they were very bitter to taste. Like oven cleaner. Do not taste oven cleaner. I want to make sure I'm very clear on that as much as I'm laughing. Back in the old day, they used to wash people's mouths out with soap when they said a naughty word. And so, yeah, maybe that's where that came from. I don't know. Now, we can do more to categorize different things. Again, scientists love to put things in categories. Think about the classification system of organisms: kingdom, phylum, class, order, family, genus, species. Chemists like to do that as well. And so one thing we do is we categorize stuff into electrolytes, and these are things that, when dissolved in water, they conduct electricity. Boop. I'll cut that out. So when they're dissolved in water, they conduct electricity. So if we take something like ethanol, and put it into water, there's no conductivity. It does not conduct electricity because it does not break into its ions. In order for electrolytes to work, we must have positive and negative charges. They have to dissociate, if you remember that word, into their ions. So KCl, for example, when you put KCl in water, you remember it breaks down into K plus and Cl minus. We get ions from those, and if we get ions, we conduct electricity, which is high conductivity, and you get the light bulb that goes ding. Okay. Now, some things, like for example acetic acid here, have low conductivity because some of it breaks down, but not all of it. So here you have nothing that breaks down. Here you have all of it that breaks down, and here you have some that breaks down. So the key thing here is to be able to categorize stuff with electrolytes into, the key here is to be able to categorize different chemicals into electrolytes and non-electrolytes. We'll talk about the one on the right here in just a couple of moments. So let's go ahead and try to get these into electrolytes and non-electrolytes. Okay. Electrolytes will be ionic. Acids, remember they start with an H, or bases. And for now, our bases will end in an OH. We'll talk more about that later. Non-electrolytes would be anything that is covalent. Now be careful here, because a lot of acids are going to look like they are covalent, but they are not. Remember, acids all start with that H. So let's look at some practice problems here. I want to know, is this an electrolyte or non-electrolyte? CaBr2, well, calcium is metal. Br is non-metal, so it is ionic. So therefore, this is an electrolyte. Right? Metal plus non-metal. CH3O, well, it has all non-metals, so I know it's covalent, and it's not an acid because it doesn't start with an H. So this has to be a non-electrolyte. HNO3, those are all nonmetals as well, but we have that H that starts there. Remember, this is nitric acid. So because it is an acid, it is an electrolyte. Again, pretty straightforward there. As long as you know how to group and categorize these things, you're going to be in really, really good shape. So as we talked a little bit about in the previous part, you notice that some electrolytes are naturally stronger than others. And that is because of how much of the material actually breaks down into its individual ions. So let's look at HCl as an example. HCl is a great example because 100% of it breaks down into H plus and Cl minus. Now, H plus really ends up actually becoming H3O plus because it reacts with water. But 100% dissociation, meaning that every single molecule of HCl breaks down into H and Cl minus. So that would make HCl a strong electrolyte. Now, none would be something, let's say oxygen. Oxygen's covalent, it doesn't break down, it's not an electrolyte. A weak electrolyte is one that only partially dissociates. So if it's weak, some dissociates. HF is a great example of this. Some of HF will break down into H plus and F minus, but only about 3% of it. So we get some that break down, but not all of it. That makes it a weak electrolyte because it only partially breaks down. You do get some electrical current with it, but it's not nearly as strong as, say, HCl, which 100% dissociates. So something that's really important here is how do we determine whether acids are weak or strong? And the key way I would go through and do this is just to memorize your strong acids. Everything else would be weak. So my strong acids would be HCl, HNO3, HBr, HI, H2SO4, and HClO4. These are all strong, meaning we get 100% dissociation. Weak is anything else. So it's really easy to be able to figure that out. All of this breaks down. It's a strong acid. This is weak. Notice we get a few of them that break down, but not all of them. Some acids, as you know, contain more than one hydrogen with them. If we take a look here, there's plenty of examples. These are known as polyprotic acids. So for example, if I just have one, that is known as monoprotic. 2, you probably realize it's diprotic. 3, tri. Now be careful here because not the strength of the acid does not directly correlate to the number of hydrogens it has. Take a look at this example here. Sulfuric acid, H2SO4, Ka value is very large. Remember that if K is greater than 1, we favor products, and therefore more of it is going to dissociate, right? If I just draw this out real quick. Right, K is greater than 1, so I favor the production of my products over my reactants. But notice that a lot of these down here, let's look at phosphoric acid, their K values are very, very small. Their K values are less than 1. And that tells us it favors production of reactants over products at equilibrium. So not very much of it's going to break down. Okay, so just kind of keep those things in mind. So now that we know how to determine acids are weak or strong, what about bases? Well, bases, you're probably just going to have to memorize these as well. So this is group 1 and 2 plus hydroxide. Okay, and it is safe to say that not all of them will be this way, but most of these will 100% dissociate. Into their individual ions. Okay, everything else will be weak. All right, so again, group 1 and 2, remember that's your alkali metals and your alkali earth metals. Neutralization reactions occur when we take an acid and a base and combine them together. One thing I just want to make sure you know here is that when you combine an acid and a base, your yield is always some form of salt and water. So that's a basic acid-base reaction. Acid plus base always yields some form of salt and water. So the definitions that we have so far are fine, but it doesn't encompass everything about acids and bases. And so a Bronsted-Lowry definition is much better. where acids are proton donors and bases are proton acceptors. So this makes it real easy to actually go through and identify them in chemical reactions because you can tell very easily what's donated a hydrogen and what's accepted one. So if I take a look at the example here, we've got H2O, NH3 produces OH minus and NH4 plus. Well, it's very clear to see here that H2O becomes OH because it takes that hydrogen and donates it to NH3. That allows NH3 to go from NH3 to NH4. So whatever donated that proton is your acid, and whatever accepted it is your base. Just taking a look at a few practice problems here to be able to figure this out. Let's look at here, we got Cn minus and H2O. So what donates the proton and what accepts it? Well, H2O becomes OH minus. So a hydrogen here must have been donated to Cn to make HCN. So this is your acid and this is your base. Same thing, I'm going to take a look at some of these other ones. H2O here becomes H3O plus. So hydrogen went from H2PO4 to H2O. So this is your acid and this is your base. Again, take a look here. What donated a hydrogen? Well, this did, because it donated its hydrogen to HPO4 2 minus to create H2PO4 minus. So this is a base. And then here, I take a look, NH4 plus and NO2 minus. Well, it becomes NH3, so this must be my acid because it donated the hydrogen to my NO2 minus to create HNO2. So therefore NO2 minus is my base because it accepted the hydrogen. Okay, pretty easy to do there. So what are some key ways to identifying weak versus strong? It's memorizing. Memorize the strong acids and strong bases. Okay. You can also look at K. Remember that if K is greater than 1, that favors product, which tends to favor dissociation. So again, sulfuric acid here, great example of that. Sulfuric acid, you know, is a strong acid because it 100% completely dissociates. So you see that here with your Ka value being very large. But as I go down here and look at carbonic acid, the Ka values are very small, so this must be a weak acid. Okay. Another way to identify weak bases as well is a lot of times they'll have a nitrogen with a lone pair attached to it. So for example, NH3 is an example of a weak base. And the reason is that that right there is very negative and tends to attract things that are positively charged, like that hydrogen ion will be attracted to that negative, and therefore will bond with it. So that tends to make this more of a base. Okay, so that pretty much wraps up all the stuff from the very first part of the unit. The next part will be more of the calculation-based stuff that you'll need to know for acids and bases. All right, thanks and have a great day, and we will talk to you later. Bye-bye.